CROOME from GreenWaves. Take it away, Martin.
Thanks. Thanks, Stephen. So I thought today, GreenWaves, we're a company that makes edge processors, tinyML edge processors. But I thought it'd be interesting to actually talk a little bit about some of the applications we've been working on in one specific area, which is uses of tinyML in building sensors. And really kind of look at, where building sensors come from, because I have a little bit of background in that area. What are the trends that have happened there, and what's the customer motivation behind these use cases, and then look a little bit towards the future. How could tinyML affect building sensors further? But really based in a practical example where we're really deploying our chips today. So I mean, one of the real backgrounds of the building industry was kind of the Internet of Things, which was kind of funny for the building industry, because building industry has been doing some kind of automation processes for a long time. BACnet, which is one of the protocols that's used for managing buildings, was designed for HVACs, for air conditioning machines, and it was created back in the 1980s. So it definitely predates all of that stuff. But basically, the availability of sensors, and also particularly the new low power networks which came out of the takeoff of IoT, have really helped to spread sensors into buildings. And obviously there's a huge amount of different types of sensors that can be used. These have got cheaper, these have got easier to package into devices. Definitely gas sensors there have changed that enormously. And really the whole building sensing control market is basically around three key benefits, which is, one is, making the building less expensive to run. The second is really making the building less expensive by not having as much building. Then there's increasing safety and security, but also reducing the cost of providing those. And then finally, and this probably plays more in hospitality and areas like that, but it does play in office buildings. It's increasing and reducing the cost of the occupant comfort. And that can be everything from cleaning to heating to whatever it might be. And obviously the final thing, which we're probably going to talk a little bit more about today, is the breakthrough in artificial intelligence, machine learning, that sensors can start to perceive, and particularly that you can use much richer data coming from sensors like images, sounds, infrared images, radar, fusions of sensors. And that's going to start allowing you to both classify what's in front of the sensor in terms of things being present, but also actually be able to detect where they are. And that means you can start counting things, which brings a whole load of other applications, which I'm going to talk about. Are there any concerns with this technology in terms of people and buildings? Yes, enormously. Both legislation and someone was mentioning earlier about the fact that we could try and convince people that all the processing is happening inside the sensor. That's actually extremely difficult to do. Even if you don't really have a network connection, which is possible to use to transfer a photo on, still people, if they see a camera, have a certain reaction to that in certain countries. And it's very geographical, so it's a very, very important point. So privacy and acceptability to the people in the building is really important. Accuracy is also important. There's actually no point in having this data if it's not reasonably accurate. And finally, cost. And the predominant amount of available market for building sensors is in buildings that already exist. And pulling cables through those buildings is a very expensive thing to do. So putting a sensor up, generally you really want it to be something that's going to be battery powered, and that will have a battery life which is a long time, because if you've got a lot of sensors and short battery life, you'll be changing batteries very, very often. In fact, people resist batteries, quite frankly, but they're okay if the battery life is as long as the sensor life, basically. So GreenWaves, we kind of invested in this area along with a partner who's making a infrared camera, and we took our processor, our GAP8 processor, and embedded an algorithm onto that, which is a CNN-based, pretty standard network. We've customized it somewhat and along with collecting some training data, to be able to start spotting people in meeting rooms and getting their position, so a classic detection. Good thing about infrared images in terms of anonymity is that they're anonymous. It's very difficult to figure out from an 80 by 80 infrared image who someone is. As you can see in this image, which is really an image coming from the sensor and the classification happening on gap. But then obviously you're only still transferring the bounding boxes, the position of the people, and we can achieve pretty low power consumption, about 4.4 milliwatts per frame per second, taking an image, processing it, and doing everything in about 200 milliseconds. Most of that energy is coming in the inference portion. Would say it's a 60-40 camera versus inference. This allows you to have a battery life on this kind of device, waking up every couple of minutes for about 5 years. And actually, the infrared treatment is pretty accurate. Infrared cameras are good because they subtract all of the background out of the room. You're only differentiating hot chairs, people, coffee cups, and so on and so forth. So that was great. We come up with this thing, but then you start hitting the real problems in actually getting a customer to be able to do this, because most of the customers who are in this space are service companies, they are servicing buildings. There are some sensor manufacturers, but mostly these are not experts in machine learning. So we built out a reference board with the infrared camera that will allow people to prototype this application, and we provide all of the designs to that so that they could build their own sensors. Along with that, we provided operational firmware, the camera control firmware, the model, the training data, the training model, so that the model can be fine-tuned towards data in certain other operational situations, plus tools for deployment planning, space planning, overlapping sensor management. All of these things were necessary for us to get to the point where we could actually have a sensor manufacturer have enough information to be able to make this device. And obviously, we're providing all of this under open source licenses. Then, obviously, we started to get some people making these devices. We now have about 5 different companies that are making these kind of sensors, and that has a really nice effect in terms of kind of building the possibility of the market, because some of these providers are willing to then sell on a package which contains the sensor, which contains the infrastructure to talk to the sensor in terms of the wireless infrastructure, and even contains UI, backend systems, web systems, which will actually give you things like live floor plan views, cleaning maps, alerts on safe occupancy levels, and so on and so forth. So where does this lead? Once you have the once you have the number of people in a room, you start having interesting things you can do. I mean, room utilization is obvious. Is this meeting room for 20 people actually having 20 people in it? If it isn't, then why don't we divide it in 2? With COVID, obviously, we moved from mostly that being the primary driver to also, distanciation, but also organizing flows of people to certain shared spaces. So if you have a shared space like a cafeteria, just by telling people that the cafeteria is full or it isn't full at the moment, that actually automatically organizes the flow of the people going to that space. And so that's a really useful way to actually cut down crowding in spaces, and very unobtrusive. Usage-based cleaning is an area where we get a lot of interest in customers who want to actually tune the cleaning service to the places which are actually getting used. Shared resource demand, the cafeteria, I mentioned that. Obviously, you can use it for intruder detection. Then once you've got position, obviously you can have desk occupancy, you can get average distance and things like this. Going further, we've also done some work on doing corridor flow, so actually doing flow tracking using the sensor, so you can count people going across the virtual barrier. Then you could add pose, which we're working on at the moment. So you can add looking at someone who's lying down versus someone who's standing up. So you get to the point where you can start to detect someone's fallen. Meeting room tidiness, if you start adding visual image, then meeting room tidiness, signs of occupancy like coats over the back of a chair or notebooks on the table, and some basic asset tracking inside meeting rooms like chairs, tables, projectors, and so on. Then adding sound, you can start to classify sounds, particularly scream detection, breaking glass detection, and so on and so forth. And there's definitely more opportunities here. This is just a start. We've been shipping GAP 8 in production now for over a year, and we're getting very close to chip availability on GAP 9. And GAP 9 will have a number of attributes that really increase these opportunities. I mean, firstly, obviously, it's an order of magnitude less power, and about an order of magnitude more in terms of capacity of networks that it can do. So you can see some of the numbers on Mobile Net View 1, V2 here. So that gives you an idea. And why would you want to use this? Well, firstly, increase the sensor battery life. We can bring down that inference energy cost. But also using higher resolution sensors so that you can clip out interesting portions of a room and do more detailed analysis on more detailed images. And then, as I mentioned in the previous slide, using different sensor sources or multiple networks and being able to use that to increase the value of the sensor and improving accuracy by using larger networks. And these are all possibilities that we're exploring at the moment with our customers. What we kind of learned about this is that some of the things that we thought were important about GAP, which is in a sense having this heterogeneous resources, but with a homogeneous programming model. So having really concentrate on the different areas of low-powered acquisition, doing pre-processing and filtering inside the I/O system, having a low-activity processing state, which really can stand by and wait for something interesting to happen, and then combining that with a compute cluster where we have a lot of flexibility in the type of models that we can run. We found that super important in this particular application. And it's allowed us to be very flexible in adding new features for different sensor customers in this area. So, you know, this is just an example of one high-value application for tinyML. But this is just the beginning, and we see a lot of different application spaces in IoT sensors, in IoT devices, particularly in hearables, with things like situation-aware, ANC, voice enhancement, and so on. And we'll be seeing a lot more of that with GAP 9. But if you want to come and talk to me about some of these things, then please come to our breakout session, which hopefully will open at 1 o'clock in room 6 to discuss this. Thanks a lot. Any questions?
Great, thanks, Martin.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. ADA Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs. GreenWaves. Himax. Imagimob. Latent AI. Maxim Integrated. Quixo. Reality AI. SensiML. Silicon Labs. Sentient. Google TensorFlow, XMOS, and lastly, silver sponsors, Edge Cortex, Hotg, and Synsense.